Okay, welcome all of you to NPTEL course on electrical machines 2. I am one of your TA, Sai Krishna. So I'll be assisting you with your tutorial problems or tutorial questions, any discussion part related to the electrical machines 2 course. Um, so yeah, I'm one of the three TAs I guess you are having. So every week I'll be meeting with you all the same day, same time on Tuesday 6 to 8, and we will be discussing the concepts you have been taught for that following week, and also I hope our discussions will help you in solving the assignment problems which you have, and also in understanding the course as a whole. Okay, so before starting our electrical machines 2 course, I'll just give a brief introduction of what you have read before or what you have been taught in previous semester. It's electrical machines 1, I guess. So in the first part of the machines, usually it's all about DC machines and transformers. Now coming to electrical machines 2, the primary focus will be on the three-phase induction machines, single-phase induction machines, and synchronous motors. These are all comes under the AC machines umbrella. Now, these will be the primary focus in the electrical machines too. And within this, before directly getting into these topics, induction machines and synchronous machines, we need to understand the basic operating principles of all these rotating machines. Before going there, we will have to see two important topics. First one is it is very important to understand windings of an electrical machines. And second part is if if there is some standard underlying principles of all the rotating machines, motors or generators, we need to understand those basic underlying principles. So then only we will be able to easily understand how a machine operates and why it is operating in such a manner. Yeah. So when we study any electrical motor or any electrical machine, we will try to draw its equivalent circuit if you remember. Even for the last electrical machines one course also, there have been a good equivalent circuits of particular machine or transformer like that. You might have remembered the transformer equivalent circuit. Now we will try to draw equivalent circuit of a transformer, and we will slowly analyze how that circuit like behaves. Like we are trying to predict the performance of a whole machine by looking at just the equivalent circuit. That's the purpose of equivalent circuit. Now we will start our discussion on electrical machines too with a very basic concept of equivalent circuit, and with that we will slowly proceed and we will get deep into our AC machines. Yeah. So let me just draw a equivalent circuit of transformer, and we will try to arrive at this equivalent circuit with the point of a basic concepts like circuit analysis and basic definitions of inductance and what is voltage induced, what is flux linkage. Everything we will come step by step. But let's arrive at the equivalent circuit with the viewpoint of basic circuit analysis. Now let me just draw equivalent circuit of a transformer. Now we know a transformer has a two sides, primary side and secondary side. I'm trying to draw the equivalent circuit which is referred to the primary side. Now definitely we will have a voltage source in the primary side. I'm drawing the okay, it will be very less small. Let me just draw it from here. Okay. I'm drawing the voltage source. Let's say we can call it as a V1. Alternating voltage source, AC voltage source. We will also see the significance of alternating, why we need an alternating source of voltage to a supply. That also we will see. And yeah, primary side, what else we have? We have a resistance and reactance. We usually name it as small r1 and xl1. We will get one by one everything. I'm just drawing the equivalent circuit itself, starting itself, and we will slowly get to this by through the circuit analysis concepts. Now, if you remember, we will have a magnetizing branch. We call it as JXM. It's a magnetizing reactance, and we are referring the secondary side resistances and reactance to the primary side. Now, similar way, there is a resistance here, and there is a reactance, and yeah, if we assume there is a load at the secondary, we will have a load here. Now this is the equivalent circuit of a transformer referred to primary side. And yeah, this is R2 and this is XL2 and this is the load. Let's say the turns ratio of a transformer is termed as A, which is N1 divided by N2. Usually, we denote at some factor we take the turns ratio. Now, can anyone tell me what will be the resistance part which is referred to the primary side? The R2 is actual resistance of the secondary side. Now, I'm trying to refer it to the primary side. Can anyone tell me what will be the actual value of R2 when it is being referred to the primary? This is our turns ratio A, and this is the resistance. So, any idea?
Multiply by a square.
Yeah, exactly. So it's a square multiplied by R2, and if it's a reactance, and if it's a square multiplied by XL2. So how you got this a square? I'm sure you remember. If not, we will discuss it in the next week. I'll ask you again. But think it's very basic principle. If you know the voltages, if you know the turns ratio and current relation. I hope you all remember it, V1 by V2 and 1 by N2, I2 by I1. With that, you will get this. You try this. If you don't get, we will discuss in the next session, but it's very simple. I want you to try it. Okay, now this is basically the equivalent circuit of the transformer. Now we will try to arrive at this particular equivalent circuit purely from the circuit analysis. We won't be using any other technique, just using the circuit analysis concepts. Now, yeah, we will keep this at the end. We will see how we will arrive at this. I'll just write it somewhere. Equivalent circuit of transformer. Yeah. Okay. Now, simply, what is a transformer? Transformer is nothing but a connection of two coils. When I say connection, important thing you have to notice, they are not electrically connected. They are magnetically coupled. So a transformer is a device which is nothing but a connection of two coils which are magnetically coupled. Now, if you want to draw a transformer, a general notation to draw a transformer. I'm drawing the core right now. Is the core of a transformer, and let's say there is a winding on the primary of the transformer, and let's say it is having N1 turns, and similarly on the secondary side, I have N2 turns of winding in secondary. These two are not electrically connected. There is no any physical connection you can see, but they are connected, coupled magnetically. Rather than using the word connected, we used to the they are coupled magnetically. Now, by looking at the circuit, you can see that these two coils have a kind of mutual coupling between them. We are slowly getting into the definitions of inductances and mutual and self-inductances. So if you see, these two coils are having a mutual coupling between them, because if a current is passing through a one coil and the flux will be created by it, and it will link with the other, and thereby it will reduce the voltage in the other. This is the very basic principle of how a voltage is induced in the coil. Like, let's say you're passing a current to the coil, and because of that current, the flux will be created with the coil, and it will link with the other coil. Important thing is linkage. Now, flux and flux linkage are two different things. Flux is just the flux will be created whenever you pass a current through the coil. Now, when the flux links with the other winding, it means when it relates with the number of turns or any other winding, then the flux links with that coil, then we call it as a flux linkage. So thereby, whenever there is a flux linkage happens, definitely the voltage will be induced. So now we will see what is a inductance of a coil. Anyone can tell me what is an inductance? Any basic definition if you remember? Resistance, we know the opposition to the flow of current. It's resisting something. So in the same way, who here can tell me the basic definition of a inductance of a coil? We daily use this word inductance, but it is very important to understand what exactly inductance means.
Opposition of magnetic flux.
No, inductance doesn't really oppose anything.
Opposition of rate of flow of current.
No. Rate of flow of current is something different,
Flux linkage per unit current.
right? Was that? Yeah, someone has said it correctly. Now, when you take a winding, then the total amount of flux that is linked with that coil for a given amount of current. So that's what the term inductance actually means. Now, let's say because of a current, let's say I'm passing current I through a coil, and the flux has been generated, and the flux has linked with a winding, and the amount of flux linked with that coil for that given amount of current. So that exactly is a inductance. Now let me just put that in terms of a mathematical expression, so you will get a even better understanding. Now usually we denote the inductance with a word L. Now L is equals to total flux linkage. Now whenever we're talking about a flux linkage, it will always accompany with the number of turns of a coil. Only individually flux doesn't link with anything. Flux means it's a flux that is generated due to the current. Now, when I'm saying linkage, it's linking with the turns. Now, divided by for a given amount of current, I'm passing I current, my flux is being induced. Now, just now I told flux linkage means number of turns multiplied by flux. If phi is my flux, and phi is the flux linkage divided by I. This is the actual definition of a inductor. Now, here for this particular transformer, now let's say we are considering this particular transformer here. In this transformer, let's take single winding now. Let's not directly dwell into double coils. I'm taking first a single coil. Now let's say it is having N1 and I am flowing a current of I1 here. Now because of this current I1, I can get a flux phi. Yeah, this here comes the important rule. Now my current is flowing in this direction, in this direction, in this direction. Now can someone tell me what is the direction of flux? Does it go in the clockwise direction or does it go in the anti-clockwise direction? It's a very basic law. I'll tell you it's a right hand thumb rule. Using the right hand thumb rule, can someone tell me the direction of flux, clockwise or anti-clockwise?
Clockwise.
Yes, clockwise. Now you see the current flowing in this direction, and if you put your four fingers in the direction of current flowing, and the thumb will show you the direction of the resultant flux. Now the current is flowing in this direction. My flux will go towards the roof in the upward direction. So the flux, another interesting property of the flux is it will always find the least reluctance path. It's like if you are going to a point A to point B and you want to reach that point B in a very small distance. So if you have a bigger route and you know a shortcut, you will always take the shortcut, right? So in the same way, flux will always choose the path which is offering minimum reluctance. Reluctance you can also assume it as a resistance. Now, if some path is providing a very minimum resistance, very shortcut path, it will definitely choose that path only. So, in the same way, we are providing the flux a path through the core. Core will have a very less resistance when compared to air. So now core, it will take the path having the less resistance, reluctance. So this is the path of the flux. Now in this path, my flux is going in this direction, main flux, phi 1. Now I will call this as a L1. L1 is equals to N1. These are the number of turns in the primary, and phi. What is the phi? Phi 1. That is linking with due to the current passing through the primary, that is the I1. L1 is equals to N1 phi by I1. Now here another concept we need to be careful about is the entire main flux which has been generated won't actually confine to the core. It means I'll show you here. Let's say this is the core I'm showing. Now here my main flux is passing. Let's say flux main. So it is a minimum reluctance path because it is going in that path. Now some amount of flux will find a minimum reluctance path here itself. So it won't take the main core path. So this whatever amount of flux it is going through in this path, it's not useful to anyone because it's not contributing to the main flux and it's not passing through the main core. So a small amount of flux will always get leaked in this way. So we are terming this flux as a leakage flux. So if this is the phi m main flux which is passing through the core, and this we can call it as a phi L. Phi L if it is a in the first winding, phi m1, phi L1. So the total flux generated is phi m1 plus phi L1, out of which phi m1 is the main flux and phi L1 is the uh, leakage flux. Now phi 1 is equals to phi m1 plus phi L1. Now if we substitute it in the above equation, L1 is equals to N1 divided by I1 multiplied by phi m1 plus phi L1. I'm just simplifying it. N1 phi m1 by I1 plus N1 phi L1 by I1. Now, in this, we are seeing two terms, and I can call this entire term as the leakage inductance. So each individual term is a one kind of inductance, and this is related to the leakage flux. So this I call it as a leakage inductance. Now, if I write the entire equation here, L1 is equals to N1 phi M1 divided by I1 plus I am giving the term for the leakage inductance. I am naming it as the LL1. Okay. Now let's say now we increase a bit more complexity and let's add a secondary coil to the same transformer. Now look at this figure and N1 and my current is flowing I1 and here it is phi 1 in this direction. Now I have introduced a secondary coil here, and if I introduce two coils, this whatever main flux, it's not phi 1, it is phi m1. Whatever main flux is, it is passing through this path only, and in the same path I have introduced another winding. Now what will happen? An interesting thing will happen here because the main path, the main flux from the first winding, it is flowing through that core, and while in that path I have introduced another winding N2, and the main flux will see this new winding being added to the core. Now what it will do? It will definitely link with the coil 2, right? But the newly added coil and the main flux are not related. The main flux, which is phi m1, is caused by the current flowing in the primary coil, but it is now linking it with the secondary coil, which is nowhere related to each other. That's why it's not a self-induced flux, but it's a mutually induced linkage. So now the term introduces mutual inductance. Now, whenever my whenever my phi m1 is flowing through the core, whenever it comes across this N2, this phi m1 will link with the coil 2, then we call it as a mutual inductance. Now I am naming it as a term M. M stands for mutual, and I am terming it as a M21. So this is L1 because of the self inductance L1 due to the first coil. Now M21 is the mutual inductance of the second coil, like mutual inductance of the coil due to the current carrying by the first coil. Now 2 is the mutual inductance of the second coil, and 1. This 1 represents in which coil is the main current flowing. Now this 1 is the coil carrying the current. Now, mutual inductance, what I will call this, inductance actually is N phi by I, turns, flux divided by current. So here the flux is linking with which turn? Secondary winding. So what is the turns ratio? That is N2 multiplied by the flux. Which flux is linking with the secondary winding? That is phi M1, main flux. N2 multiplied by phi M1 divided by the current. Definitely it's because of the coil carrying the current I1. Now this is the formula for the M21, which is the mutual inductance. N2 phi M1 divided by I1. Now this time let's pass a current through N2 as well. Let's make it even more complex. I am trying to pass a current I2 to the secondary coil as well. Now similar kind of behavior will happen. Now I will just write the total equations here. Flux, that is the main total flux generated by the secondary coil, let's say it is phi 2 total, is equals to, again there will be a main flux and there will be a leakage flux. I am calling the main flux as phi M2 and the leakage flux as phi L2, right? Now what will be the inductance formula for the second coil, L2? You can simply relate from the above formula. Phi M2 multiplied by N2 divided by I2. Right? Now related to the phi L2, it will be N2 phi L2 divided by the I2. Now this is nothing but the LL2. It is nothing but the leakage inductance. Now if you write it in terms of total equations, L2 is equals to N2 phi M2 divided by I2 plus LL2. Now this is the second equation we get, and the first equation will be, let's mark this as the first equation. L1 and L2, we got the both inductances in the both coils. Now I hope you all understood the inductance concept. Now let's try to relate the concept of mutual inductance. Now a very interesting thing we can see here is, if you calculate the mutual inductance for the second coil and the first coil, they will turn out to be same value. That we will see here. Now from the both equations, I will just show you how we can get that. I am taking both L1 and L2 from 1 and 2 equations. I'll just quickly write here. L1, what we know, L1 is equals to N1 phi M1 by I1 plus LL1, leakage and self, and L2 is equals to N2 phi M2 by I2 plus LL2. I seriously request you all to also take a pen and paper and solve these simple questions with me. It will keep you engaged, as well as you can also solve it along with me. If I make any mistake or something, you can quickly prompt me. Okay. Now these are the two equations we got, and what we know that the mutual inductance from the previous slide. How much is the mutual inductance? M21 N2 phi M1 by I1. M21 is equals to N2 phi M1 by I1. Now similarly, what will be M12? This is the mutual inductance of the coil 1 due to the current I2. Now N1, it will be linked with the first coil due to the main flux in the second coil due to the current flowing through that I2. Now I will call this equations 3 and 4. Okay. Let's take equations 3 and 4, and can someone tell me the formula of flux? If you know flux, if you know MMF, if you know the reluctance, what is the formula for flux?
Sir, MM by reluctance.
Exactly. Now flux is equals to MMF by reluctance. R relates the reluctance. Now I am trying to calculate the mutual inductance using all these relations. Now assuming a linear magnetic field, reluctance will always should stay constant, and for the same core. If the core remains same, reluctance will always remain same. Now, you see M21 and M12. I took these two equations and I'm trying to replace the flux you see there with the mmf by reluctance formula. M21 is N2 by I1 multiplied by phi M1. What I can write phi M1? Phi M1 is the main flux in the first winding. MMF means ampere turns and then Ni is mmf. Now, in the same way, phi M1 will be, anyone, can someone tell me what is phi M1? N1 I1 by reluctance. Reluctance is same in the core, so I'm not marking it as R1 and R2. If I assume a linear magnetic field, R should stay same for both because on the single core we have wound these both windings. Now, okay, M21 is this, and let's write the similar kind of expression for M12. M12 is N1 by I2 multiplied by phi M2. Phi M2 is N2 I2 by reluctance. Now, if we see the both expressions, the current terms get cancelled and I2 get cancelled, I1 get cancelled. Now, M21 comes out to be N1 N2 by reluctance and M12 comes out to be N1 N2 by reluctance. Aren't these two same? M12 is equals to M21 is equals to M because both are same. So no matter what, if you are winding two coils on the same core, whatever current you might pass through each core, each winding, I1, I2, whatever values you take, as far as the turns ratios you know and the reluctance you know, the mutual inductance will always be same for the both windings. That's what we have seen here. Now, from where we started our discussion, so we started this discussion whether we can arrive at the equivalent circuit of a transformer using the basic concepts of electrical engineering. So we started with inductances. Basically, we start what is an inductance, what is the formula of inductance. We derived all the self inductances, mutual inductances, and now we will see the concept of voltage induced, and further we will go into the other topics, and we will eventually arrive at the equivalent circuit. But one more important concept in the magnetically coupled coils is dot convention. All these are very important in getting to the equivalent circuit. That's why I'm going it one by one.
Yes, sir. How
Yeah,
to write this leakage inductance
sorry. So you're talking about where this leakage inductance comes into picture.
reluctance?
Uh, I didn't get your question.
Leakage inductance.
Yeah,
How to write in terms of Ni and reluctance?
uh, leakage reactance comes to the air reluctance, right? You have to take the reluctance of the air there, and I don't think it links with any terms like if you have let's say N2, for the same winding, if you have a winding N1, you know the turns ratio N1, and you have to actually calculate the phi L2, that is flux, leakage flux. Leakage flux will be mmf by reluctance, and you take the turns ratio of that particular winding, and the current will be the current flowing through that winding, that is I2, and the reluctance will be, you have to take the reluctance of the air, not the core, because that's not passing through the core. So yeah, that's how we can calculate the leakage leakage inductance. But while calculating the mutual inductance, leakage won't take any part because mutual is between the main coils, and it is caused by the linkage of main flux with the opposite coils. So there is no concept of leakage in actually calculating this mutual inductance concept. So yeah, let's have a look at the dot convention. I know many people will have confusion in dot convention. Some feel dot convention very simple, but yeah, if you understand how the dot convention happens, it's really very simple topic. Now, let's not draw the complete transformer, but I'll try to draw a transformer in a simple way. So this is primary and secondary. This is N1 and this is L2. This is inductance of the coil L1 and L2, and let's say we have a mutual inductance which is having same value just we just saw M. Now, one important thing which we are going to discuss now is the dot convention and dot convention. And let's pass a AC current, alternating current I am passing. So, anyone tell me the reason why only alternating current I am trying to pass?
Sir, because direct DC currents will not induce any EMF.
That's correct, but you have to tell me the reason why it doesn't induce any EMF. Exactly correct, but what's the reason behind it?
Sir, induced EMF depends on the rate of change of flux, sir.
Right.
And in DC the flux remains constant. Well,
Yes, correct. Now, to actually get a whatever our one of our attendees said, I'm trying to put that in the words. Now, to get a let's say voltage to get some kind of induced voltage across any two terminals, what we need is a time varying flux. Time varying flux means your flux should vary with respect to time. So at each point of time, the flux would vary. Now, to get that kind of flux linkage, you have to like which is changing with respect to time. Then only your induced voltage will appear across the terminals. In order to get that kind of time varying flux, you need to pass a time varying voltage. Sorry, time varying current. So to get that kind of current, you should have a alternating voltage as a supply. So let's pass a AC current, and I'm sure if I pass a AC current, I will get a uh, alternating voltage, alternating flux I can get. So the flux is varying with respect to time, and I can get a induced EMF. Now, when I pass a AC current through a core, the plus minus terms will always be alternating with respect to time. I'll just draw it here. This is the core of a transformer, and this is the primary winding through which I am giving the alternating voltage. Let's say this is called V1, and if it is, let me just write it as a time varying quantity, V1 of t. Now, let's say the current flowing through is I1 of t in this winding. Because of this current, a time varying flux will be generated, that is, I am calling it as phi m1 of t. If there is a secondary winding existing here, there, if at all some current needs to be reflected in the secondary, I need to connect a load. Let's say I have connected a load here. As soon as I connect a load, current will pass, right? Now my question is, what should be the polarity here? Let's say these are the load points. I am connecting a load here. Is it plus or minus? Let's say it's case A, or minus plus. It's case B. Any idea what is this, case A or case B?
sir, A, sir.
It's A. Okay. Now, yeah, if you are saying the answer, you should also explain me the reason why it is A. It's correct. You can also explain to your friends here.
Sir, if the voltage are induced according to the option A, sir, then the currents will try to induce a flux in the core that will oppose the flux which has caused this voltage to be induced in this coil, sir.
Exactly.
It will follow Lenz's law.
Yeah, it's exactly Lenz law. Now, Lenz law, what it says is the effect should always oppose the cause for which it's due. Now, the cause is I have passed an alternating voltage in the primary winding, right? You can see I have passed a primary alternating voltage in the primary winding. Because of that, I have caused a alternating flux to generate, that is phi m1t. Now because of that phi m1t, it is linking with the secondary coil and it is inducing a voltage across the secondary coil. That induced voltage is happening in the secondary coil. That is the effect. What is the cause? The cause is the flux. What is the effect? The effect is the induced voltage being generated. Now, here the effect should always oppose the cause. My induced voltage should oppose the cause, which is the main flux. Now, in order to, when I say opposing, it should go in reverse to each other. Now, if it's a positive and negative here, positive and negative means let's say first let's take it the minus and negative, negative and positive case B first. Now I took positive here and I took negative here. Now positive means current will flow through like this because this is a load, and load, the current will flow like this, and the current is coming like it. The current will flow, and current will flow like this. Now if the current is flowing in this direction, and just if current is flowing in this direction in the secondary winding in this direction, what will be the flux direction? Right hand thumb rule. If it is this direction, and flux will be towards the down. Now my secondary flux generated will be in this direction. It is phi m2 of t. Now this is taking this path inside the core. Now this is this path, right? My flux is generated in this path phi m2. If you see the phi m2 and phi m1, both are in clockwise direction only. Phi m1 of t is also in clockwise. Phi m2 of t is also in the clockwise direction. But what do our Lenz's law say? Your effect should oppose the cause. My flux generated, this should always oppose the main cause, which is phi m1t. So I don't want the flux to be in this direction, but I want my flux to be in this direction. So in order to the flux go upside, my current should flow in this direction. In this direction means my current should be going into the load from here. It should pass through the load and it should come back like this. So whenever it is plus and minus here, it should always be plus and minus like this. Now I'm just, if it is plus and minus at primary, and it should be plus and minus at the secondary. I'm talking about load here, and here it's a supply. Now in the negative half cycle, it's an alternating voltage. Now in the next half cycle, it's minus here and it's plus here. Now in the same way, when it's minus and plus, then it should be minus and plus at the load side. So that's why it's always alternating. If it's plus here, if it's plus here, if it's at this instant, if you see, if it is plus, and here it's also plus, and in another instant, if it's minus, if it's also here, it's also in the minus direction. So instead of representing the plus plus minus minus, since it's always alternating, we have kept a common symbol. That's a dot. So that's how the dot convention came. So if you see a dot anywhere, the dot always represents the polarity of a terminal at that instant of time. Let's say okay, at this instant of time, the polarity of the terminal is plus. Now if you see the same dot in the next secondary side, the same polarity also exists here. That's what the dot represents. Now whenever you see two kinds of dots here, you can instantly say that, okay, at this instant of time, if I know this is positive, and I can blindly keep this also as a positive, even if I don't know the voltage and current flowing through here. If I know, if I am sure that the primary side is positive at the dot, and the secondary side is always the dot, because the dot I can see it should have the same polarity. If it's minus, then it is minus. So that's what a dot convention actually represent. Now let's see another interesting concept related to the equivalent circuit. We are slowly moving towards the equivalent circuit. We have learned about inductances, dot convention, and now we will see the KVL equations, and we will slowly put these three together, and surprisingly we will reach the equivalent circuit very easily. So Yeah, I hope dot convention is clear now. Even now, we will get even more clarity in the dot convention. Let's take the KVL equations of primary and secondary side. Now, well, we will take the KVL of each side and then we will simplify it, and surprisingly, we will have the equivalent circuit equations that we will see. Now, let me just draw a nice transformer here. This concept, if you understand this concept, the coming numericals which we will be solving in the later half, it will be very easy. Now, I also want you to um, like seriously listen to this concept because it will make your problem solving session very easy. Okay. Now there is a primary winding here and there is a secondary winding here. Okay. Now I have given a alternating voltage V1 plus and minus. At this instant I am marking it, and it is causing a current of I1 to flow through this N1 turns, and we have N2 turns here. Okay, now let's say this is A and B. I'm keeping a dot here, and this junction I'm calling it as a C and D, and here I'm placing a load to which I want to deliver my current Z. Okay, Z2 I can call because I'm giving it as an N2, and I have placed a dot here because since it's a plus and minus, and since it's a dot here, and here will always have a plus and minus at this instant. Now the dot is here and the current will flow here, I2. Sorry. Okay. Now let's assume these windings are having a kind of resistances with them. So any winding may not be very pure conductor, it will have its own resistances. I am taking those resistances as a R1 of primary and R2 as the secondary resistances we have. Now I can show entire resistance of the wire as a small lumped R1 and entire resistance of the secondary as a lumped R2. Now let's try to make the KVL equation for the primary side of the winding. Now in this primary side you can see a voltage source is there, right? And there is a flux generated that is phi m1, that is due to the inductance L1, and there will be a mutual inductance that is due to this secondary current flowing through, and that will be all the kinds of voltages that you can see in the primary side. Now that's what I'm trying to draw here. I'm having a main voltage source, that is the main supply voltage, that is V1, and I'm trying to represent the other two voltage sources. One is self-inductance and one is due to the mutual inductance. Here in primary winding also there will be an induced voltage will be there. Anyone tell me why there is a induced voltage in the primary? Because your primary coil is being subjected to a time varying flux, and that will in turn induces the voltage. So that's how the supply is being balanced. Now I'm trying to write that particular voltage plus minus. We'll come to the polarities, and in the electrical convention, you know, like when there is a d by dt, you usually mention it using a j omega. That is the notation you use, because the voltage, if you see the n phi by minus d by dt of n phi, so you can get that d by dt, you can replace it with the j omega. Now if you see, you have, I'm writing the self-inductance term now, and j omega, that is d by dt, you can say L1 I1. Now there is a another voltage source caused due to the mutual part. Mutual always due to the current flowing at the secondary coil, right? Due to I2 current, this mutual inductance voltage is being induced. Now that is J omega d by dt. The mutual will have a M. There is no M12, M21. Both are having the same value. And the current will be I2. That is J omega M I2. The polarity will come. Polarity will come when it is a using the dot convention. We can simply mark the polarity. Now, I also know that these two coils are having a mutual inductance, and due to that mutual inductance, this particular another source I have come, it is J omega Mi2. There is bound to be another voltage induced because of this mutual inductance. Now, what is the polarity of the J omega Mi2? Can someone tell me? So this is a bit tricky, and if you clearly if you carefully see the this particular circuit diagram, and you can simply say the polarity of this J omega M2. Is it a plus minus or a minus plus? So this particular A and this is B. If you see, this is A and B, and I'm trying to get the polarity at the B side, at this point B. What is the polarity at the B? Is it positive or negative?
So B plus A minus.
That's correct. Then, can you quickly tell me how you got the positive at the B?
Sir, by using a dot convention, sir, the unmarked terminal D,
Yeah,
the current is entering.
right.
Therefore, this current will induce a current in coil 1 such that it will come out from sir, terminal B.
Yeah, right. So if you see the terminal D, here I have marked dot convention at A and C has a dot, and the unmarked terminals are B and D. Let's say I have a square convention here. Now I need to understand the terminal at the B. Now if you see the square at here, the current is entering. Now what is the polarity of the side at the primary where the current is entering? At this instant, here the current is entering the dot, here it is plus. So the same polarity will be there where the current is entering at the secondary side. So here the current is entering at the D and it is plus. Now at at this box, since the current entering at the box it is positive, so the polarity at B, that is the same box, because both are having the same boxes here. So simple dot convention. So the polarity at B will also be a positive. Now that's how you can get the positive sign here and the negative sign here. So yeah, you just have to see wherever at whatever joint you are trying to find the polarity. See if the same polarity exists in the other side. If you know the polarity at the other side of the same box, then you just blindly put the positive or negative at here. So that's how simple the dot convention is. Now, similarly, this is the primary side equivalent circuit, right? This is the,
Yes, sir.
yeah,
Can we say it like another way? Because in C, the current is leaving the dot,
yes,
so the mutual voltage, because of this change in the current, the
huh.
primary side will enter the dot.
uh, no, no, yeah. If you are trying to backtrack it, yeah, I
Yes.
mean, if the current is leaving from the C, yeah, the cause due to that C is entering at the dot. So yeah, that's also okay. Uh, but you should not do like that, because you know the polarity at the input side, that is I1. So from there you are giving the source will always supply, and its current is always entering the dot. Now because you have a load at the Z2 and current should leave the dot, because it should oppose the main flux, so from there you have to get the polarity of B and D. Yeah, okay, this is the primary side equivalent circuit. Now, similarly, if you try to do the secondary side equivalent circuit, and I have a load here, that is Z2. Okay, Z2 is can also be represented as a voltage, that is V2, which is nothing but the I2 and Z2. I'll just represent this is V2 here, and this is plus and minus and V2. And because I know there's a current is flowing through the Z2, it's a V2 here. And here again, I will have two voltage sources. One is due to the self-inductance, that is J omega L2 I2. Similarly, J omega L1 I1, I have J omega L2 I2. Polarity is same, positive and negative, same as this one. And now I have a mutual part. So what is the notation of it? J omega M, because of the primary current I1. Now with the same understanding, what is the polarity here? I can say the current is entering here, I2. I want to know the polarity at this instant. So it is what? It is D, the C. Current is entering D. So yes, Dinesh.
It's plus upside, sir.
Here,
Yes, because the current is entering the dot in the first side.
yeah.
So the mutual coupling due to this effect, the secondary side, the current will be leaving the dot. How it can leave? If it is only plus upside, then the current can leave there.
No, no. You already know the current is entering the dot here.
No, in upside secondary side, the current is leaving the dot.
You mean this dot?
Yeah,
Okay, okay. Yeah, here it is leaving, but at the D side it is entering.
yeah.
So it's a positive or negative here now. Uh, at the D, you tell me it's positive or negative at the D.
It is negative
Why it is negative?
because in the primary side, the dot, the current is entering the dot, and this mutual coupling to secondary is caused by the primary side.
Okay.
So they, the current should leave the dot. The how it will leave? If the positive is there upside, negative is there, then only it can force the current to leave the dot.
I didn't understand that. Okay, actually, the you are saying okay, okay, okay. Yeah, now I got your point. Yeah, if in order to the dot from the primary side, the current is entering the dot, and in this side, the current is leaving at the top. But the bottom side, if you see the polarity at the D, it should be negative because the current should uh, like since it's the dot here and which is entering there, and here at the D it should always be leaving, and that's why it can't be the same polarity. It should be leaving, then only you will get that kind of flux. Yeah, sorry, I didn't get what you are I couldn't clearly understand, but yeah, whatever you're saying is correct. So it should be a negative sign for the mutual side at the D, and it should be positive at the yeah. Yeah, so since we now have the equivalent circuit of the secondary and also the primary, let's just quickly write the KVL equations. Now, simple KVL. Now, yeah, primary KVL. Can someone tell me V1 is equals to, yeah, there is a small resistance I show. This is the R1 lump resistance. If there is an R1 here, and V1 is equals to, let me, yes, okay, V1 is equals to I1. Yeah, this current is of course I1, and this current is of course I2, and V1 is I1 R1. That is first voltage drop you can see, plus j omega L1 I1 minus j omega M I2. That is the KVL equation for the primary side. Now, similarly for the secondary side, if you see now, this is the secondary. I can start from here. J omega L2 I2, and I started from the self inductance part, and we have this particular minus J omega L2 and minus J omega L2 plus I2 R2, and there will be a V2 plus V2 minus J omega M I1 is equals to 0. So yeah, it's a simple two KVL equations, and once again I'm just to get more sheets. Yeah. So now yeah, we got the two KVL equations, the both sides. Now let's try to uh, replace this whatever equations we got with the equivalent terms. We will replace the inductance whatever present in that with the inductances. Now I'm just writing it again here. V1 is equals to I1 R1 plus J omega L1 I1 minus J omega M I2. Now V2 plus J omega L2 I2 minus J omega M I1 plus I2 R2 plus V2 is equals to 0. Okay, already wrote V2 is equals to 0. Okay, now these two are the voltage equations. Now what we know from the I'm just trying to replace this inductances whatever L and M and this inductance parts. I'm trying to replace it with, let's keep it this M as it is, but we already know what is L1 and L2. We solved from here. Now what is the formula for L1? We got self inductance for plus leakage inductance N1 by M1 by I1 plus leakage LL1. Now if I'm trying to replace this flux, what can I can like, I'm just trying to wait. I'm trying to replace this flux term. So what I will do, I will divide by N2 and I will multiply by N2 here, N2 I1 plus LL1. Now can someone tell me what this N2 phi M1 by I1 is? We have just solved that. Okay, let's go back. N2 phi M1 by I1, that is nothing
Mutual
but
inductance.
mutual part. Yeah. So let's replace this entire part with mutual. And what is N1 by N2? That is the turns ratio, right? A, and this part is M plus LL1, that is L1. Now similarly, if you get the expression for L2, it will be M divided by A, because for M2, N2 will be in the numerator, plus LL2. Now we got L1 and L2, and we just take these L1 and L2 and we'll substitute in these two equations, 1 and 2, and let's see what happens, and we can simply get to the equivalent circuit. Now, okay, V1 is equals to I1 R1 plus J omega L1 is AM plus LL1, AM plus LL1 into I1 minus J omega MI2. Okay, J omega MI2. And if you see the second equation, now I'm taking this term J omega into L2. L2 is M by A plus LL2 into I2 minus J omega M I1 plus I2 R2 plus V2 is equal to 0. Okay. Now we will just simply take common from just some algebraic manipulations here and there. We see that this equation will become V1 is equals to I1 R1, that will remain same, and I'm taking J omega AM as common. I1, this I1, and from this here I'm taking J omega AM common, so there is no A here, so it will be I2 by A. Okay, and what is the term left? That is J omega leakage term, J omega LL1 I1. Okay, just drawing a line here. Yeah, similarly the second term, I'm just taking the term J omega. If I multiply with A here, AM plus A square LL2, again I'm dividing it by the A. If you see, is the same term here, I2 by A minus J omega AM I1 plus I2 by A square R2 plus I2 by A square Z2 is equals to 0. I just multiplied the entire equation with A, additional A. It's just to get the terms same as the equivalent circuit. You will see why I did that. Now let's draw the equivalent circuit for the primary. If you see, there is a voltage source from this equation V1, and then there is a I1 R1. So I'm just trying to represent it as a R1, and I know the current flowing through it is I1, and there is a kind of I1 minus I2 by A. It's like a loop current. So this particular J omega AM, it is sharing with I1 as well as I2 by A current. So we will keep that for us later. And there is another series current which is J omega L1. This is J omega LL1. Okay. Now this particular term which is sharing the branch, there is a J omega AM. So here it is I1, and here it should be I2 by A. Can someone tell me the direction of I2 by A? It should be up towards like clockwise or anti-clockwise?
Sir, clockwise.
Yeah, it should be clockwise. Then only it will be the negative of it. I1 minus I2 by A. Okay, now we have approached the secondary side because all terms on the primary are completed. Now if you see the secondary side, there is a square R2 because I2 by A is the current. That's why I divided and multiplied by A to get the I2 by A every side. Okay. Now if I say the first term will be A square R2. This is A square R2 term, and then we have another I2 by A term which is this one. If you see the I2 by A, there is a A square J omega LL2 term. A square J omega LL2. Okay, and there is a just load term which is this one, I2 by A multiplied by the A square Z2. Okay, now whatever left term, if you see, this is J omega AM which is having I2 by A minus J omega AM I1, I2 by A minus I1 which is tallying with this particular magnetizing branch. So you got the equivalent circuit of transformer which is referred to the primary. Of course, everything we are seeing it from the primary side. Now this is nothing but the equivalent circuit of transformer refer to primary. Isn't this the same circuit we have started with? And let's go back to the first slide of today's discussion. Now there is a voltage source R1, XL1, we are calling it as a leakage reactance, and there is a magnetizing branch JXM. Now it is J omega AM, and there is a secondary side A square R2, A square XL2. Here it is A square omega L LL2, and the load which is A square Z2. So we have arrived at the equivalent circuit. So we have not used any complex topic of any transformers. We didn't try to establish anything, but we have just arrived at this equivalent circuit by looking at the basic circuit analysis concepts. So our first one we have seen inductances. One second, someone has joined. Okay, we have first seen the definition of inductance, what is self-inductance, what is mutual inductance, and we then proceeded for the dot convention to understand the polarities, and then we saw the KVL equations, and just that's it. We have arrived at the equivalent circuit of the transformer. So I hope you all understood this concept of equivalent circuit of transformers, and we can do the direct numericals based on it. But before that, I want to discuss a very small topic, that is energy storage in coupled coils. It's very small topic. It's very simple also. Uh, uh, let's say you have two coils, and if you want to find the kind of energy stored in the coils, because inductance always stores the energy. It's unlike resistance. Resistance always dissipates the energy, right? Now let's see this small concept of energy storage in coupled coils before we move to the numericals based on these exact concepts we just discussed in this today's session. Now, let's say we have a single coil. This is a single coil, only one coil. I have passed small current here, and this is the inductance of the coil. Now, we know what happens. The voltage will be induced, and I am trying to represent it as a two voltage sources, right? Till now, that's what we have done. And this is V of t, and this is the voltage, and this is the induced voltage L di by dt. We are writing it as a j omega, right? L is voltage, and this is the current flowing through it. And let's say these are the terminals of A and B. Now we can see with respect to the source, the current is leaving the source. I mean, at this point, we see if this is the source, and if this is the dot, and the current is leaving the positive terminal. Let's just talk in terms of positive and negative, then no confusion. But the current is leaving the positive terminal. So what it is, the current is being supplied by the source. Whatever the energy, whatever the power that the load is seeing, it is being supplied by the source. So there is a energy is being sent from source to the load. So that's what we are trying to establish here. Now if you try to calculate the instantaneous power, instantaneous, why I called instantaneous means instantaneous always say it's the power at that instant of time, because after some time it might be some negative value, alternating voltages, alternating currents may come. So I always take instantaneous, because at that point of time we can analyze the circuit. Now if we calculate the instantaneous power, that is small p is equals to voltage at that instant and multiplied by the current at that instant. Is simple. Now if you see the load from the load side, if you see the inductor side, so this particular inductor side, if you see the current, it is taking inside. It means it is the current is being absorbed by the inductor. You can say absorbed. The current is entering its this positive. From this polarity, if you see the current is entering in this positive, so it's being, we can say the current is being absorbed. The power is being absorbed by the L. Now the power absorbed by the inductance L is called, let's say at that instant of time, you are trying to find the di by dt we have. Now at that small dt of instant you are trying to see. Now the power absorbed by at that instant is dp. Now if you see, yeah, what is dp? Again, the voltage induced at that point of time. And what is this voltage? This particular L di by dt, L into di by dt multiplied by I. I is same because it's a current, same current is flowing through it. In time dt, the energy absorbed by L will be, because I'm trying to convert this power into energy. Energy absorbed will be dW omega, like W usually noted by the energy. Now d omega is nothing but power multiplied by dt. Now power I already know, which is L di by dt multiplied by I whole multiplied by dt. Then you get the power into wattage. Now this dt gets cancelled. What you are left with, dw is equals to L I di, right? So if you integrate this entire energy over the entire range of current, you will get the total energy absorbed by this particular inductance. Now I'm just trying to integrate it. Now dw is equals to L I di. Integration of dw, I'm integrating entire current with respect to di. So what are the limits of this current? It can go from 0 to I. In this 0 to I, the maximum value of current. Now if you integrate it with L 0 to I, you will get the half L I square. So what you got, this is the energy stored in the inductance at that instant, like through the instantaneous equations, you integrate it with whole to get the total energy absorbed by that inductance. So this half Li square. Now, what will be the energy if there are more than one coil? So this is for one coil we saw. If there is only one coil. Now, what will be the energy if it's a coupled coils? It's similar and simple. Let's just quickly look into it. Now there is a one coil here, and there is another coil, and V1 of t, that is plus and minus, and here is another source V2 of t, and this is plus and minus, and the current will be in this, because this is supplying current and this is supplying current, the both L's are taking the uh, current into them, both are absorbing. Now this is I1 and this is I2. So usually not according to dot convention, it's not according to dot convention. We are assuming there is a voltage source and it is supplying the inductance. Now if I try to draw the equivalent circuit for it, there is plus and minus here, that is voltage, and there is current being sent, and there are again two voltages, right? One is due to the self and one is due to the mutual, and the same polarity will be for the self, that is L di1 by dt, of course, and there is a mutual part, M di2 by dt. So di2 on the primary side, and we will see the polarities quickly later. But now just let's first write the conventions. L2 di2 by dt, and this is M di1 by dt. This is L1, and yeah, now we know this is positive and negative, and this is V1 and this is V2. Okay, now see the polarity of this M. What is this plus and minus? And now I'm trying to get the polarity here, and this polarity is in this way. It is leaving here. Here entering is positive, so leaving is negative. Here it's also leaving, so it should be negative at this instant. So it is negative and it is positive. And if you are trying to get the polarity at this instant, you are trying to get at this instant. And if here the entering is positive and leaving is negative, so here also you are trying to get the same instant of where it is leaving. So here it is negative and here it is positive. So here it is anyway plus and minus. So that's how we get the equivalent circuit at the both sides. That is the if you are assuming two sources at the both side. Now, again, simply calculate the instantaneous power absorbed, that is small p. Now we have two coils here, and looking at the uh, this part, only this part we have seen, not the source part. So this part and this part, voltage multiplied by current. What is the voltage? We have two voltage sources, L1 di1 by dt, M di2 by dt, that is being taken by this current I1. Now that is L1 di1 by dt plus M di2 by dt, that is taken by I1. Now one more absorbing part is this one. This is taking the current I2, L2 and M. L2 di2 by dt plus M di1 by dt, that is due to the current I2. Simple. Now again, let's convert this into the energy, that is P into dt, and you just have to multiply by dt. All dt's will get cancelled. L1 I1 di1 plus M I1 di2 plus L2 I2 di2 plus M I2 di1, right? Now we know in the mathematical notations, I1 di2 plus I2 di1. You know what you call that, right? There is a mathematical formula for it. I'm just trying to simplify it. L1 I1 di1 plus then this part L2 I2 di2, and if you take M common, this entire I1 di1 plus I2 di1 will be, you can represent it as a di1 I2. Okay. Now this is a mathematical formula. Now the energy stored from the entire duration when the current changes. Now in the coil 1, we are trying to integrate it. Now we are just trying to see the limits. Current will change from 0 to I1, and in coil 2, current will change from 0 to I2. These are the integrating limits. Now the W total energy absorbed is L1, this part. I'm integrating, this is I1, right? 0 to I1, I1 di1 plus L2, 0 to I2, I2 di2. Now for the M part, we have both currents. So it's a I1, I2, di1, I2. Yeah, again simple. This will be the half L1, I1 square. This one is half L2, I2 square. And this one will be M, I1, I2. Okay. So that's it. Yes, Neeraj?
Sir, this formula is derived assuming that both the sources are operating at the same frequency, no, sir?
Yeah, yeah, of course.
If the frequency changes, then the formula will change.
Yes. Frequency, we don't get into that kind of complexity. Like you are supplying the same source at same frequency, you assume it. Yeah. Because then the mutual inductance will also be affected. So there is a frequency term comes into picture. You're right. Because the omega term changes, right? Omega is nothing but 2 pi f t. The omega will change. So yeah, this is the total energy stored in the entire coupled coils. Half Li square relates to the self inductance of the only due to coil 1, half L2 I2 square due to coil 2, and due to the coupling mutual, there will be an extra storage, you can see, that is M I1 I2. So yeah, this is a very simple and easy concept of energy storage in coupled coils. Now let's quickly look into the questions, and there is half an hour left, and I require all your active participation. Just take a pen and paper with me, and we will solve these questions. These are very simple questions. If you have understood the discussion, of you have got the concepts clear for the last 1.5 hour discussion, these are very, very simple. Now take a pen and paper along with me, and let's solve the questions. Now let's read the question. We have a question number 1. So we have two coils of an ideal transformer. Ideal transformer means, right, there are no leakages. There is no very ideal transformer. Yeah, someone join. Okay, we have an ideal transformer having two coils labeled as AB and CD. Yeah, you can see that AB and CD from the figure. Now these two coils have 300 and 200 volts respectively. Now terminal A of coil AB is marked with a dot. Right. Self-inductance of coil AB is also given, that is 3.6 Henry. Now the two coils are connected in series. So this is something we have not discussed, but it's nothing to be worried about. Series connection of coils and assuming negligible leakage flux. Of course, there is no leakage flux ideal transformer. And the question is, which terminal of coil CD should be marked with a dot? Okay, now we have a transformer. Okay, now we are passing. Okay, let's see. We will start with the basic.
C, sir.
Okay, right. Let's solve it together. Right, it's C. Okay, I'm trying to pass a current here. My current is entering the dot. So if it is entering dot here, my current is like this, and current is like this, and my flux generated will be like this. The current flux will take its path, and flux will go this path, and flux will return its path. Now, if you see the flux, I'm asking a very important question, very important question you have to answer. So the flux now like the flux generated or the flux responsible for the coil 2 should be clockwise or anti-clockwise. So here we have seen a anti-clockwise flux from the first side, and what should be the flux in the CD coil? It should be clockwise or anti-clockwise.
Anti-clockwise. Sorry, clockwise. Clockwise.
Why it should be clockwise?
Maybe as per Lenz law.
That's everyone. Definitely Lenz law will be there, but important thing we have to observe here is Lenz law is applicable in magnetic circuits where the coils are magnetically isolated because the cause and effect are opposing each other. Now here if you see, these two are series connected. They are not magnetically coupled anymore. So they are in a series connection. This connection is simply like this one. There is two connections, and this is A, and this is B, and this is D, and this is C. So this is how the connection is. So they are not magnetically coupled and they are not electrically isolated. They are electrically connected. Now, with this convention, we have found that this flux is in this direction. Now these are series connected coils. Now in a series connected coils, the flux always aids each other. If this is series and this one also series in this direction only, right? So this particular series connection will make all the difference here. So the flux, that is to get the same like the flux in the CD coil also is a anti-clockwise flux because the both coils are in series connection. Okay. Now tell me, I hope you understood this anti-clockwise concept. Everyone, yeah, it's a very general thing to think that if the coil in the AB is anti-clockwise, definitely the coil in CD should be clockwise to oppose the effect. But no, oppose the cause. But it's not like that because they are not magnetically coupled; they are electrically connected. Now, this is the anti-clockwise. Okay, right. To get the anti-clockwise flux in the CD, the current should enter at C or D. Look at the CD coil, and I need to get a anti-clockwise flux. So I need to have a current like this, right? This is the current I should get. Then only I can get a anti-clockwise flux. Now, if it is like this, the current should be entering here. The current should be entering the C, and the current is leaving the D. Right. Now tell me, if you know the polarity of A, that is dot, here the polarity at which the current entering is dot. Now, similarly at the secondary side, the dot polarity, yeah, Neeraj,
So due to this series connection, the current direction will be reversed as you have marked, sir, in the second question. Please see for one. So current is entering from A, leaving from B, going into D, and then coming out of C due
actually,
to series connection.
no, actually, it happens to be current should enter C. It will come like this, and it will come like this, and it will come like this, and leaves through B. This is how it should be. Then only this anti-clockwise flux can be generated. Or if it is AB, okay, yeah, definitely, yeah, it should be. If it is like this, yeah, there's it is connected, and it will go like this, and it will leave through D. AB, and it will do this, and from here it will leave through D, and it can't enter from this side because the current should enter at C to get anti-clockwise, right? The current direction won't change within the windings, but through the series connected path, the current will flow in this direction. But if you see the CD coil, the current should flow in this direction. Okay, as the current entering at the A is dot.
Sir, I want to say something.
Yeah,
No, this you're telling the series connected. I'm
yes.
saying it like these both the points are at the same potential,
Which one? B and D.
B and D.
Yeah, B and D at the same potential.
So only the point that remains A and C, so
Yes.
whatever the polarity of A is there, the C will have the same polarity.
Yeah, same polarity. Right.
So means and the lens, it is a magnetic circuit.
Yes.
It is still a magnetic circuit.
Yeah, but there is no uh, concept of main flux opposing the flux in the CD, because here the flux linkage concept, like the whatever flux linkage happening in the second coil, it's due to the main current only. There is only single current flowing through it. One second, someone has joined. Yeah, and what I'm saying is, here whatever flux that is causing in the CD coil, that is also due to the same current. So that's why there is no concept of two different fluxes opposing each other. Whatever fluxes we are seeing are both aiding each other because they are causing by the same current. Yep. So at the C, the current enters. So at the same dot, the dot will be at the terminal C. Okay. Uh, let's see the question.
One thing more, sir.
Yeah.
Suppose I reverse the sequence of the winding here.
What will you reverse?
Suppose it is a like anti-clockwise. I reverse it like clockwise.
If you are
Sequence of the winding. Like
okay,
C comes up and D goes down.
C comes up. C is already up now.
No, on the core. Start.
Okay, okay. C comes up and goes down. And if C comes up, that is the current will have a clockwise, so it can't be in this direction. And current should leave the C.
Yeah, same thing.
Uh, yeah, current should leave the C then.
Leave the C, but dot will remain there. Like winding is clockwise, suppose, then I make it anti-clockwise.
I understand. If the winding is anti-clockwise, okay. If the winding is anti-clockwise, then to get an anti-clockwise flux, Okay, to get an anti-clockwise flux, the current should leave the C, right? So if it's leaving the C, then dot can't be at the C.
But B and D are a force at the same potential. These are physically connected.
Yeah.
But then only the A will be the same dot at the C.
Okay. Don't think so. Maybe the current direction will change at the D point. This is D you are saying, and this is the C, and I want an anti-clockwise, and this will be my current, and yeah, and this will be D. And if I see the uh, dot, and here it's connected to D, the current should enter D. Okay, so this point, and current will enter, and it will leave through C, and from here we already have a current coming like this, and current will come like this, and it should, yeah, it will take this path, and it will do like this, and it will come, and this it will leave like this. Okay, now in that we have to mark the polarity of I mean the dot should be at the D, I guess, but B and C have the same potential. Yeah. Okay, that's a
Sir, the dots are marked according to how the flux are linking both the coils, sir. So for marking the dot, we have to ignore this series connection from B to D, and we have to only focus on the flux that is flowing in the core. Then we can see that terminal C would be with a dot mark.
okay. No. If we ignore the in this connection, you are saying the dot in this.
No, sorry, in this figure, sorry, which
Oh,
is on the slide, sir.
that's okay. But in this direction, the dot will be at the D, right? Because the current is leaving C. At the D, it is entering. I'm sure that dot should be at the D.
Sir, for CD side,
Yeah.
first of all, to find the and we have considered current or flux to denote the dot for dot. First, what we have considered? Direction of current of CD coil or flux?
I'm,
First of
I'm,
all.
I'm considering the direction of the current only. Like, is the current entering the dot? Is the current leaving the dot?
Okay.
So, if at one side the current is entering, if that's a dot, and in the secondary side, wherever the current is entering, I will place the dot there. So, that's the dot convention. Yeah, if whatever Neeraj is suggesting, like if we ignore this series part, if we consider only the current entering and leaving part, because that's what the flux is causing. Now then I will definitely say that the current is entering at the D, then I can mark dot at the D for this condition. So this condition, I know it's clear at C, but I will look into this part whether it is like that or it's something else, and it's definitely a discussion point for our next week.
Like physical wire connection,
Yeah,
so the potential time response will remain the same.
yeah. Potential, I understand the concept, like potentially it's at the same potential, but are we talking about the voltage potentials here or the dot conventions individually? Okay, definitely we'll look into that. I'll bring up this point again for the next session. Meanwhile, you also have a thought about it. And yeah, now let's look into the second question quickly. We only have 10-20 minutes left. Now, suppose we are giving a 150 volts RMS to the AB side of the coil, and now and this coil CD is left open. Okay, there is nothing is connected. There is no load connected, and the two coils are connected again in the series as shown. Now we have to calculate the RMS value in volts between the A and C. So, okay, somehow they are giving a AC of 150 volts, that is RMS at the A and B, and they are leaving a CD open, and they are asking us to calculate some kind of voltage drop across the AC between the terminals AC. Oh, can't you see my presentation? Is my presentation visible?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Okay, Shanti, you might have to maybe rejoin and come back. Try that. Yeah. Okay, so we are trying to calculate the voltage between the terminals A and C. Okay, let's say I'm giving some 150 volts, and somehow there is a potential difference is being developed between A and C. I'm trying to calculate the VAC. I'm assuming positive and negative. I know it could be anything, but I'm just assuming. If my notation is wrong, at the end we will get a negative sign. So we'll see. And okay, this is C and D. I'm assuming this is a polarity in the CD side, and input I have a 150 volt supply, and it's just a anyhow B and D are at same potential, and I'm just trying to calculate the VAC. So it's simple KVL. If I apply, what I will get, minus 150 plus VAC and plus VCD is equals to 0. That's KVL. Now VAC will be 150 minus VCD. So if I can get the value of VCD, I can easily get the required potential difference. Now VCD is nothing but the secondary voltage. AB is nothing but the primary voltage. Now how can I calculate the secondary voltage if I know the primary voltage and also the turns ratio? So a simple notation. Now V1 by V2 is equals to N1 by N2. Now this is VCD and this is VAB, and I know N1 and N2. Now V2 is equals to V1 into N2 by N1. Now V1 I know 150 volts RMS, secondary turns is 200 and primary turns is 300, and it will come out to be and 5 and 100 volts. Yeah. Now VCD is 100. If you substitute here, now the required VAC will be 150 minus 100 is equals to 50 volts. It's very simple. You just have to strike the point. Like I have the turns ratio, I know the voltages. How can I get the voltage with that notation? Okay. Now we have to estimate the self-inductance of coil CD in Henry. I think they have given us the self-inductance of coil AB in the question. Yeah, it's 3.6 Henry. Let's just write here L1 self-inductance is equals to 3.6 Henry. Now they are asking L2. How much is the L2? Okay, we have anyhow know N1 and N2. Now, can someone tell me the formula for self-inductance, which we have already derived in our discussion? Okay, let's get back. No issue. L1, where is L1? Yeah, L1, this one. L1 is N1 phi M1 by I1 plus LL1. I'll write like that. N1 phi M1 by I1 by plus LL1. L1 is equals to N1 phi M1 by I1 plus LL1. But in the question, what it was given, it was an ideal transformer, and we have to neglect the leakage resistances, leakage reactances. So whatever negligible leakage flux, there is no leakage now. Now I am neglecting this. This is 0. Now L1 comes out to be N1 phi M1 by I1. But here to calculate the flux, you have to get the MMF by reluctance and everything, etc. You need to get. Now what is the M phi M1? I can replace this flux in the first coil by MMF, that is N1 I1 by reluctance. I1 will also be there. So I1 will get cancelled. N1 square by R. So L1, which I already know, which is 3.6, is N1 square by R. Now similarly L2 will be what? N2 square by R, right? So you someone joined. Okay. Now with these two equations, I know L1, I know N1, I know N2. It's simple. Now take the ratio of these two, L1 and L2. L1 by L2 is equals to N1 square by N2 square, because reluctances are same, they will get cancelled. Now L2 is equals to L1 into N2 square by N1 square. So 3.6 multiplied by N2 square, that is 2. 4 by 9. How much is this? 1.6 Henry. Simple. Again, it's just a relations between voltages, turns ratios, and MMF reluctances, everything. You, this all formula should be at your fingertips while solving these questions. And for the gate also, these are very important topics, and they can give for a very 2 marks, or small questions. You can just have to solve it in 1 mark. Anything. Simple formulas. These magnetic circuits can able to solve it very fast. Okay, now, okay, we have already estimated the self inductance. Now they are asking us to estimate the mutual inductance between AB and CD. Anyhow, the mutual inductance will be same value, and I'm just writing the formula here. L1 I know, N1 square by R. L2 I know, N2 square by R, and mutual is N1 N2 by R. Right? Okay. You can take ratio of any two if you want M. So you can take L1 by M or L2 by M. Anything. I'm taking L1 by M. L1 by M is equals to N1 square by R multiplied by N1 N2. So you will get cancelled, and N1 by N2. And so yeah, M is equals to L1 into N2 by N1. So L1 is 3.6 and N2 is 200 by 300. And how much is this? 2.4 Henry. That's it. Again, a simple numerical adjustment. Okay. Our last question for today. It's related to the energy stored in the coupled coils. Yeah. Now we have a 2 amps DC current is being passed through the two series connected coils. Then how much energy will be stored in the two coupled coils? Now, what is the formula we know? Energy storage for the coupled coils, half L1 I1 square plus half L2 I2 square minus M I1 I2. Okay, now if you see, these are series connected, and now, okay, this minus or plus, we just have to decide it based on whatever convention we are taking. That's how we will get. And these are now these are series connected coils. Now this could be like this. Now there is a supply. It is given for in the primary. 2 amps is being flowed. Now let's say 2 amps being flowed here. I can write this circuit like this, and there is a this is a connection, and secondary is connected like this, and this is how it should be. Now current is flowing like this, and this is B, and this is A, and current will come, and since it is open, the current will go in this way, and current will leave from this C and D. This is how the current will go and leave. Now if I try to get a equivalent circuit for this, like equivalent voltages, if you want to, there is a self inductance and there is a mutual inductance, and this is plus minus. If I say, this will also be plus L di1 by dt minus, and this will be the mutual di2 by dt. So what will be the potential at here? So if I see this current is leaving from this box, and if it is entering here, and here it is entering, here it entering, it is plus here, so it will be plus here. Now Okay, we are trying to find the energy that would be stored in the two couple coils. Now, if I combine these two, like in the same way, if I draw the circuit for the secondary side also, how it will be, I'll just quickly draw the primary side, and then for the secondary side, there will also be two, and, and there will be some voltage in the output and the current, and this will be, let's say if it's V2, I'm just seeing the what will be the secondary side absorbed and what is the primary side absorbed. And here two amps DC, they are flowing into the both connected coils. So the 2 amps will flow in this current also, in this winding also, in this winding also. So there will be a voltage at the secondary side as well as the primary side. Now this will be J omega L2 I2, and this will be J omega M I1. Okay, then the potential, if you see at this potential you want, and here it is the current is entering, and here the current is entering, and it will be the plus and it will be the minus, and here also it will be the plus and minus, anyhow same potential. J omega M I2, this one, this is will be J omega L1 I1, plus and minus. Okay, now you got all required. This is the 2 amps that is flowing here, that is the I2, and this is the I1, same current. Now, you know, each voltage, as if you see, E1 induced will be, someone joined. Okay, E1 will be L1 di1 by dt minus M di2 by dt. Now, E2 will be L2 di2 by dt minus M di1 by dt. Now, if you solve this particular entire same thing which we did there, we'll get half L1 I1 square plus half L2 I2 square minus M I1 I2. So this potential will change based on, sorry, the potential will change based on the current entering or leaving. So there we assumed the current being entered, and here also we have assumed the current is entering, so this potential will be minus. Now it's just you have to substitute all the values. You know L1, you know L2, you know mutual, and you know I1 and I2, which is same, 2 amps. Then you can get the total energy store. So you can just simplify it and substitute and get the answer. It's not that difficult. Okay, now that's all for today. I want to discuss these concepts with you. And if I just take you through a quick summary of what we have discussed today, we started our discussion with what is introduction of this electrical machines 2 course, which we are going to discuss today, like for the entire course this semester. And we started with a equivalent circuit of transformer, and we tried to arrive at that equivalent circuit by using the circuit analysis concepts. We started with inductance of the coil concept, and then we derived self inductances and mutual inductances, and then we looked at the dot convention, and then we started deriving the KVL equations, and finally we got arrived at the equivalent circuit. And then just we looked at a simple concept of energy storage in the single coil, and then we extended it to a couple coils, and we derived the expression for energy storage in the coupled coils, and then we started solving the numericals based on these concepts. So please let me know if you have any doubts in today's concepts, or anything you want to ask on the discussion we had done today.
Sir, I want to ask something.
Yeah,
Sir, like in this, the 2 ampere DC current is flowing in the
yeah,
problem.
yes,
So the DC current flowing will cause the minus M I1 I2, that there is no time varying effect, sir.
okay. No,
So if
when
anything,
you are integrating it, uh, you will only have one current here. DT terms will anyhow get cancelled in this energy storage. DT term won't appear at
no,
all.
in calculation of the energy, sir,
Yeah,
because the M I1 I2 comes from the time varying effects.
both L1 di1 by dt, M di2 by dt also comes from time varying only.
Now, now they are series connected. Na?
Yeah.
The current is flowing DC current.
Yes.
So there is no mutual coupling in between them.
Coupling will always be there.
Sir, there is no time varying effect here. The coupling comes from the time varying flux change in the flux. It will be
No,
half Li square plus half Li square.
I don't think
Because
so.
DC current is flowing, the self inductance will store energy. That will also, but whether the AMI1 I2 will come or not. Because there is no mutual, when I am flowing DC current, there is no mutual.
Mutual current, no, if they're series connected, that's okay. And if you are having a two different coils, and I think okay, there is a due to the current flowing through the I2, there will definitely be a oh, no, the secondary flux will link with the primary, right? Even though they are series connected, the flux will be induced. Whatever flux flowing through the secondary, it will interact with the primary winding or not. That's what mutual. There is no time varying. Time varying discussion is not there, right? There is a flux is being generated because of the current flowing through it, and yeah, the flux linked with the primary turns, and then that's causing the mutual effect. While calculating the E1, I can say there is no di by dt at that instant of time. So if you look at two different instances, definitely there is no change in the current. So di by dt will, there is no sense in taking the di by dt. But when you look at the energy, on total energy you are calculating, that in that concept dt concept is itself is eliminated. We looked at the derivation. But whatever you are saying, whether it's a DC or AC current, the mutual, I think mutual will exist because the flux is being passing through both coils. AB have a flux and CD have a flux. That's what I think. Okay, anyhow, I will look into this. If it's a DC current, what happens to the mutual part? Will it be there or not? I'll look into this and I'll get back to you.
An
But
RMS current, then it is okay.
yeah,
It's an
RMS.
RMS current, then it is okay.
Okay, RMS means okay. That's another discussion. AC part. Okay, I'll see that. What's this? The mutual comes or not? Okay. Okay. Apart from that, anything else today? I think it's pretty forward, pretty straightforward concepts we discussed today. And moving forward, we will even get deeper into electrical machines too. And I hope you all will attend for all the future sessions. And it's a very good discussion, interactive session today. And I hope we keep this pace for the entire 12 weeks of the course. Okay, I request everyone to go through the lecture videos taught by our professor and also try to solve the assignments and try to submit it before the deadline. And yeah, assignment two with the next week we'll also discuss that. And 7th is the deadline for that, I guess. So before that, we will try to attend all the concepts and yeah, let's meet next week, same time, same day on Tuesday, and see you all next week. Thank you for patiently attending and listening to me and having a good discussion with me. Thank you all.
Okay. Good night, sir.
Good night. Thank you.
Thank you.
Thank you.
Thank you.